In this video, we're going to practice exponential and logarithm derivatives. Now, we've seen in a previous video how to find the derivative of the exponential function e to the x and the logarithmic function ln of x. Now we're going to look at other exponential and other logarithmic functions based on this fact. If you want to follow along, the links to the companion worksheet are in the description below. So let's get started. Now with this first one, we can see right off the bat that we have a logarithm that we want to take the derivative of, but it's log base 4, not ln. ln is log base e. And so the first thing we have to do is we have to apply the change of base formula that we saw in pre-calculus. And that is, well, how would you calculate this on a calculator? Well, the way you would type it in is, all we know how to do is ln of x. And so that means that has to be part of our expression. To find the derivative of log base 4 of x, we would take ln of x and divide that by ln of 4. Now this puts it in terms of a logarithm of a derivative, logarithm derivative that we can find. So now if we can find this derivative, we can find the derivative of this because these are equivalent expressions. Now one thing we can do is we can recognize that ln of 4 is a constant. Because it's a constant, we don't need quotient rule here. What we can do is we can rewrite this as ln of x times the quantity 1 over ln of 4. Now that's helpful because ln of x is not a constant, but 1 over ln of 4 is a constant. So that means all we need is to find the derivative of this, and then because this is a constant, it will just cling for the ride. So dy dx is going to equal the derivative of ln of x, which is 1 over x, times 1 over ln of 4. Now that will simplify to 1 over x times ln of 4. Now it's important to put the x in front of the ln of 4. If it were behind, some people would be tempted to think that the denominator would be ln of the quantity 4x, but it's not. So we want to write it like this. So now, if we look at the second one, here we have log base 5. But here we have this expression x squared minus 1. So what we first want to do is let's put this in terms of ln. So in terms of ln, this would be ln of x squared minus 1 all over ln of 5. Again, this is still just f of x. We're just rewriting the expression. So now we have ln and ln. Now ln of 5 on the bottom, that's still going to be a constant just like it was in number 1. But here, when we take this derivative, this is going to involve a little bit of chain rule. Now first, let's rewrite this with ln of x squared minus 1 out front times 1 over ln of 5 separately. Just so we remember, that's a constant, so when we take the derivative, we don't have to worry too much about it. So the derivative, f prime, is going to be the derivative of the outside. So the derivative of ln is 1 over x squared minus 1 times the derivative of the inside times 2x times, now we still have this quantity 1 over ln of 5. So when we put all of this together, the 2x that was multiplied goes on top. Then we have x squared minus 1 times ln of 5. So there is our derivative for this. So now, looking ahead to number 3, here we have a log, but there's no number. Now the convention is that when there's no number, it's understood that that number is 10. So now we can rewrite this as ln of 9x cubed minus 8x all over ln of 10 So then we'll separate out the ln of 10 off to the side so that we remember that it's just a constant and we don't have to worry about it when we take the derivative. Put that in parentheses. So f prime of x equals, now this again involves chain rule, so it's going to be 1 over the inside function, 9x cubed minus 8x times 27x squared minus 8 times 1 over ln of 10. So when we put all of this together, we have 27x squared minus 8 on top. On the bottom, we have 9x cubed minus 8x times ln of 10 on the bottom. Unfortunately, if we look at the top, there's no factors that we can take out of this, and there are no factors we can take out of this. So this expression cannot be simplified. This is as simple as we can get for this derivative. Now looking at number 4, this is just the generalized rule for any log with any base, where a is just any constant. So if we follow the pattern that we have used already, we're going to rewrite this as ln of x over ln of a. And again, a is a constant, so like we did before, we can separate out ln of x and 1 over ln of a. And so the derivative, dy dx, is going to be 1 over x times 1 over ln of a. And when we put those two together, we have 1 over x times ln of a. And so that right there is the generalized rule for any logarithm where the base is not e, where the base is some other number. So those were the logarithms. Now let's take a look at exponential functions. So here we have the derivative, we have the function f of t equals 4 to the t power, and we want to find its derivative. Now unfortunately, can't really find that because, well, the only thing that we could do is if it were e to the t, but it's not. But what we can do is we can say, well, let's just rewrite 4. Let's leave the t exponent out there. Let's rewrite 4 with e. Now we can raise e to some power to get us 4. The question is, what is that power? Well, without a calculator, we do know that, well, that power would be ln of 4. Now most people would say, well, that would just cancel out and be left with 4. Yeah, but we want to leave it in this form. We want it as e to the ln of 4. Now here it's got 2 exponents on there. Now what we can do is we can combine them. E to the t times ln of 4. Again, no derivative yet. All we've done is just rewritten it. Now we have e as our base, which means now we can find the derivative, f prime of x. So the derivative is just that, e to the t times ln of 4 times, well, now it's chain rule. So chain rule says whatever the inside function was, which is that, we take its derivative. Now t is our variable. ln of 4 is a constant. So that means this is the same as 3t or 10t, except the constant is ln of 4. So when we take this derivative, the t falls away, and we're just left with ln of 4. So here we've got this derivative, but let's simplify this a little bit. Here we've got e and we've got ln of 4 again. So let me separate out those two powers. And so here we've got e raised to the ln of 4, which would just simplify back to 4 to the t power times ln of 4. So when we have 4 to the t power, we end up with 4 to the t power, which is kind of like e, except we have an extra constant times ln of the base times ln of 4. So looking down at number 6, now we've got a bit of chain rule here. Now if this were 9 to the x, we could just substitute out 4 with 9, and we would have 9 to the x times ln of 9. But because of sine of x, that makes this a chain rule problem. So we'll write this as u equals sine of x, and y equals 9 to the u power. So when we write, we're going to have to find the two derivatives of these separately. So du dx, that's the derivative of this part right here, is equal to cosine of x. And dy du is equal to 9u times ln of 9. Now I got this just by using the pattern that we had up here. So now to find the derivative, what we do is we multiply these two. dy du times du dx equals 9 to the u times ln of 9 times cosine of x. Now what happens down here is that the du's cancel, and so we're left with dy dx. Now we have to pull out the u and say, well, what was u? Well, we set u equal to sine of x. So 9 raised to the sine of x times ln of 9 times cosine of x. So let's look at the next one. This one also is a chain rule question because we have 3 not raised to the x, but 3 raised to the x squared power. So we can write this as u is our inside function, that's x squared, and y is our outside function, which is 3 to the u power. That's what we substituted out x squared for. So our derivative du dx is equal to 2x, and dy du, again using the rule, the pattern that we had from number 5, that's going to be 3 to the u times ln of 3. So to find the derivative altogether, we're going to take dy du times du dx. So we have 3 to the u times ln of 3 times 2x. And as with before, the du's cancel. So we have dy dx equals 3 to the x squared times ln of 3 times 2x. So now, if we look at the last one, we want to find the derivative of a to the x where a is a constant. So basically, I'm just going to follow the same steps that we did in number 5 right here, except we're using a instead of 4. So we're going to rewrite a in terms of e. So that's e raised to the ln of a. Now since we have two exponents, we put them together, x ln of a. And so now what we can do is we can take this derivative, dy dx. So we have e to the x ln of a. But remember, we have to take the derivative of this inside function because it's not just x times ln of a. And as with number 5, we can pull these two exponents apart now and say, all right, well, e to the ln of a, that e and ln will cancel back out, and we're left with a to the x times ln of a. And so that's the rule anytime we have a derivative that isn't e. It's similar, it's that base to the x power, but we also multiply on an ln of that base. If you liked the video, please give it a thumbs up. For more videos like this, please click the subscribe button. If you have suggestions or problems you want to see worked out, type a comment below. If you want to support the channel, click on the Patreon link to help keep this going. Thanks so much for watching, and remember, the only way to understand something is to do it.